Hi everybody, welcome to physics. It's Mr. Duffy, and today's lesson is going to be about static equilibrium. To do that, we're going to start off by talking about net force, finding net force. Now, I talked about this in the first lesson in this unit. We talked about the law of inertia. So the law of inertia, we had to add up our forces, and again, if the net force was zero, it's just going to keep doing what it's doing. And so that's kind of where I'm going to kind of continue on here with us. Basically, the net force, the sum of all the forces acting on an object, is the net force total. And for static equilibrium, that net force is going to come out to be zero. So the sum of the forces is going to come out to be zero. But we're going to, again, talk about that and get to that point here in a second. So how do we find the net force? Well, in the previous problem, we didn't have any numbers to that free body diagram, but imagine scenarios where we do. When we have the individual forces that we can use, basically we just add them up. We resolve them into x and y components, and if they're at angles, and then add them up to see what their overall net force is. So here we have basically 4 newtons to the north. We would say that is positive 4 newtons because it's going up. We denote that as positive. And that would be a negative 4 newtons going down. So the overall net force would be 0 newtons. That's the basis for finding net force. Now, obviously, that's an easy problem. So is this one, but this one does not end up with a 0 net force. It ends up with, again, we have 6 newtons to the right. We normally say that's positive. We have 12 newtons to the left. We normally denote that as negative. And so our net force would be negative 6 newtons. Or we could say 6 newtons to the left. That would also be an acceptable answer. So again, that is finding net force. Now you can imagine the scenario where we have more than 2 forces. In this example, we have this free body diagram where there are 5 different forces acting upon it. But again, it kind of just, again, resolves itself down. These are all in the x and y directions. So we have a positive 5 and negative 5. Those cancel out to the horizontal. And then we have 2 down. That's negative 2. And then we have positive 1 and a positive 3. That adds up to 4 newtons total up. And so that we would end up with 2 newtons up as our overall net force. So again, we could just resolve it into the x and y's, and this one again, just entirely x and y's. Now we might also have a story problem, in which case we're trying to find the net force of an object. So it says a gust of wind blows an apple from a tree. As the apple falls, so the gravitational force on the Newton or on the, on the apple is 2.25 newtons. So 2.25 newtons here, and that would be the weight of the apple or the gravitational force. And then the force of the wind is 1.05 newtons to the right. Well, this is our first problem where we've come to, where we have, they don't, again, resolve each other into x and y. We have a y direction and an x direction, but not, not total, not the x's or the y's aren't canceling each other out. So what we're going to do is we're going to turn this into a right triangle, which again is totally fine. 1.05 newtons to the right and 2.25 down. We want to find that hypotenuse. We want to find the magnitude and direction, since forces are vectors, to find the the overall net force acting upon the apple. So let's find the magnitude first. A squared plus b squared equals c squared. We're looking for c. C is going to be the hypotenuse, so 1.05 squared plus 2.25 squared, and then the square root of that. Comes out to be 2.5 newtons. That is one of the answers, not the entire answer yet. We also need a direction, so let's find that angle there. I think the easiest way to find that angle would be tangent. So tangent, -1, so inverse tangent of my opposite over adjacent. Opposite is 2.25 over adjacent 1.05. That'll get us our angle. So you could have used any trig function though. We get an angle of 65 degrees. So that would be 65 degrees south of east. There we go. We have a magnitude and a direction. So finding that force can still be, again, very similar to some of our like motion problems. So again, nothing new in terms of trig functions here. Now, let's get back to where we were focusing on for today, is the fact that objects in equilibrium. So the law of inertia says an object wants to keep doing what it's doing unless it gets acted upon by a net force. Well, equilibrium means that there is no net force. Basically, again, the objects are either at rest or moving with a constant velocity, so the net force acting on the object is equal to zero. Basically, what that kind of sets up to our problem, if we know that, again, the net force is the sum of the forces, like again, like force 1 plus force 2 plus force 3, however many forces there are. But if we know that this always comes out to be zero, the sum of the forces, if we know it's an equilibrium, then we know all these forces are going to add up to zero. So again, maybe I have force 1, and I have force 2 is, let's say, 20. I know that force number 3 has to be negative 30, that's basically how it works out. So again, I would be able to figure out, since I know that it adds up to zero, I know that my final force is the remainder. Okay, so let's put that to practice. Here's a problem where we've got, again, x and y values, and we're, again, looking at equilibrium. So I have 6 up, 6 down, so those, again, are going to cancel each other out, positive and negative, and we have 8 newtons to the right and 8 newtons to the left. The overall net force is 0 newtons. I guess I could have written it a little bit differently. I didn't, but I could have. So maybe, let's see, I'll just erase some of the stuff. We can imagine a different scenario of the same problem. Let's just say I've got, and to fill it. Okay, so let's just say I just made this up, but we already know the answer, obviously. But okay, so it's that maybe we know that the net force is 0 newtons entirely. So the question might be, what is the force to the right? So again, we have 6 newtons up, 6 newtons down. We have 8 newtons to the left. Again, by doing that, we know that would be 8 newtons to the right. That would be, again, another good example of a net force type of problem. Static equilibrium. Again, another word is static equilibrium. There is another type of equilibrium we'll talk about in a later chapter. So again, this is static equilibrium, balanced forces. Okay. Okay, so for our last problem that I'm going to show you here is going to be very similar to your problem that you're going to do on the assignment, except for I'm doing a level 2 problem, and I'm going to assign you a level 1 problem. So it should be a little bit easier for you, hopefully, but it will be different. So you just kind of have to think about how you're going to do the problem. So here we have a weight that is 2.6 kilograms, and it's hanging by 2 different ropes, rope 1 and rope 2. The red rope is rope 1, and we're trying to find the forces of tension in those 2 ropes. They are both suspended vertically, um, or at an angle from vertical, I guess, from the ceiling. And it tells me in the problem that this angle is 31 degrees. So 31 degrees to the vertical, and they're identical to each other, which means that the tension in these ropes is going to be identical to each other. So that's going to kind of be important for solving this problem. So to be in static equilibrium, the forces up and the forces down must be equal, the vertical forces, and the horizontal forces must be equal as well. So let's think about what is the force down. Well, the force down is the weight from the mass that's hanging. The weight is calculated by taking the mass 2.6 times gravity. So we're going to multiply those two together to get the weight of the to get the force pulling down. Okay, 25.5 newtons is pulling down. So that is going to also equal the weight going back up. Now, again, that's going to be the total weight. So maybe if I draw it over here as like a free body diagram, we have 25.5 going down. But you can imagine that it's really kind of like 2 weights or 2 forces going back up, because there's one from each rope. And so there still is total of 25.5 going up, but then each one of those would be 12.25, if that makes sense. So there's 2 of them that are identical to each other. I didn't really write that well, so let me try again. So again, there's 2 arrows, one from each rope, each one of them is 12.25. Okay, and then that would add up to, again, 25.5. Okay, so let's just imagine again, if I'm just trying to solve for the force tension of one of these, the red or the green, it doesn't really matter because they're going to be identical. Then the triangle here would be 12.25 for the vertical. And the horizontal force, I don't really necessarily even need to solve this. I could solve for it and then use the Pythagorean theorem, but it actually be just easier if I just use some trigonometry here. So hopefully you all agree that this angle on the inside of the triangle is 59 degrees because the angle outside the triangle was 31. So that adds up to 90, and so the angle inside here is 59. I have my opposite side of that angle, and I want to find my hypotenuse, so that's going to bring me to sine. So sine of 59 degrees is equal to my opposite, which is 12.25 divided by my hypotenuse. So again, I'm trying to find my hypotenuse. So I plug that in my calculator. And I'm going to get a hypotenuse of 14.3 newtons. And that is going to be force tension in this triangle. And since the other triangle is an identical triangle, it's also going to be the tension in this triangle as well. 14.3 newtons for the hypotenuse there as well. Okay. And so I would enter that into the program. It would tell me if I'm correct or not. And again, if I was correct, I would post a screenshot of it just like I've done in other assignments in the past. Again, this is a level 2 problem. Your problem is going to be a little bit different. You're going to have one of the ropes is going to be at an angle and the other one's going to be completely horizontal. So I'm going to ask you to think a little bit about how that one's going to be done.